almost any kind of fat or oil can be used to make biodiesel. The great majority of biodiesel in Europe and in this country are made from these two oil seeds, rapeseed in Europe, soybeans mainly in North America. There's another cultivar of rapeseed that recently has become more popular in North America. It's got the name of canola. And although most of it's being used for food products right now, it certainly is possible that someday it could enter into the biodiesel market. We'd rather say canola than rapeseed for some reason, although rapeseed's name is derived from the Latin word repa, which means turnip. Anyway, the reason that these oil seeds are used is that they're extremely high in fatty materials called lipids, and in particular in long-chain fatty acid-derived compounds called triglycerides. And the chemical formula of a triglyceride is shown on this slide. As you see there on the left, there are long carbon chains that are esterified with glycerol. And to release the biodiesel from this product, we use methyl alcohol or methanol and a base like potassium or sodium hydroxide. And the product that's formed is glycerol, it's kind of a waste product, it's water soluble, and these fatty acids and methyl esters. And some of these are straight chain saturated compounds like stearate. Some of them are unsaturated, double bond containing compounds like oleate and linoleate. And we'll get to some of those later. Biodiesel, pure biodiesel, which has nothing in it but fatty acid methyl esters, is called B100. And although it's not very commonly used, more commonly used the B5 to B20, the low concentrations of biodiesel together with larger amounts of petroleum-derived biodiesel. It turns out that biodiesel can be mixed in any proportion with conventional diesel oil. We have chosen to work with pure, more or less pure biodiesel. We haven't gone petroleum-derived products yet. One problem with biodiesel is that when it's stored, it develops what's called oxidative damage. And what this involves is the addition of oxygen to the, especially the unsaturated fatty acid methyl esters. And it turns out, for mechanistic reasons, the most highly unsaturated fatty acid methyl esters are most readily attacked. The fatty acid linolenic acid, which has 3 double bonds, is the most rapidly attacked, followed by linoleic acid, which is the most abundant fatty acid in soy biodiesel, and oleic, which has only 1 double bond, is much slower. But in any event, when this oxidative damage begins and continues, the resultant biodiesel is much less useful for using in engines. Even under ambient conditions, biodiesel degrades. The red line is a measure of oxidative damage, and the black line is the temperature for a given day. And you see those temperatures are in the range from 10 to 25 degrees C, ordinary summertime temperatures. And even during storage for a couple of months, there's a pretty significant amount of oxidative damage by this biodiesel, which is B100. The reason this happens is that there's a radical chain mechanism that's involved. And shown there in the unsaturated fluid, like the linoleic acid that I showed in an earlier slide, these particular unsaturated lipids are particularly susceptible to being attacked by what are called initiators. And the initiator shown there, OH dot, is what they call a hydroxyl radical. It's by no means the only thing that can carry out the initiation, but for convention we'll show it as the initiator. And what happens is the initiator, free radical, abstracts the hydrogen atom, which means it goes to the water. And the product then is a lipid radical, carbon-centered, what's called a carbon-centered radical, where the free radical is on the carbon atom. When this radical is formed, if there's any oxygen there at all, there's an extremely rapid, practically diffusion-controlled reaction with molecular oxygen from the air. And the product of that reaction is the lipid peroxyl radical. And the lipid peroxyl radical can also abstract the same kinds of hydrogen atoms from the unsaturated lipids. And the product of that reaction, OOH, is a lipid peroxide. The lipid peroxide is also a fairly reactive species, although it's not a free radical. I want to point out these two species, the peroxyl radical and the peroxide, are the most important compounds that are involved in the oxidative damage of biodiesel and many other kinds of hydrocarbon polymers. What happens when the lipid peroxyl radical abstracts another hydrogen is you go back to another lipid radical, and the whole process goes around and around. The first step, the initiation step, is a slow step generally, and the propagation step is a fast step. There's another step that we'll see in some of our later slides where the lipid peroxides break down and go to other kinds of oxidized products, acids, carbonyl compounds, aldehydes, a whole variety of oxygen-containing species. And that is called the termination phase. We'll see that later. In fact, here it is. Free radical chain reaction kinetics, as I described, begin with the slow initiation step or lag phase that's shown here. This particular slide happens to be about bacterial growth. It turns out that the same thing can be used to describe free radical chain reactions. The lag phase or initiation phase is slow, but once it starts to take off, the log phase, which we call the propagation phase, goes along at a very fast rate. Oxygen is taken up by the fuel. The peroxide concentration goes up. There is a point then, somewhere along the line, where there isn't any more material left to react with the peroxyl radicals, and that's more or less a stationary phase. And then the peroxides, either peroxides, start to break down in the termination phase. So to counteract this process, compounds called antioxidants are used. And the two I want to focus on, the first two, the peroxyl radical quenchers and peroxide destroyers. Now these compounds are very different. The peroxyl radical and the peroxides are very different in their reactivity, and the antioxidants that are used are also very different. The peroxyl radical quenchers are known as chain-breaking antioxidants because they stop the propagation phase from going on. The peroxide destroyers work on the initially formed or the subsequently formed peroxides and reduce those back to alcohols. There are other kinds of antioxidants that work by different mechanisms. The chain-breaking antioxidants are usually phenolic compounds. We call them DHT and DHA. Those are the synthetic chain-breaking antioxidants that are quite reactive. But vitamin E, or alpha-tocopherol, occurs naturally. But when you look at these phenols, they all have similar structural features. Looking at alpha-tocopherol, you see the OH or phenolic hydroxyl, and it's flanked by two methyl groups, which are just shown as lines in this drawing. But that makes this compound what we call sterically crowded. The product that results from the chain-breaking antioxidant reacts with peroxyl radicals is also a free radical, but it's a fairly stable, sterically crowded radical that doesn't have much chance to go on and react with some other compounds. BHT is really sterically crowded because those adjacent groups are tertiary butyl groups. Those are 3 methyl groups that are next to the OH, and butylated hydroxyamazole, or DHA, has 1 tertiary butyl group. So both of these antioxidants are effective because the radical that results from the quenching is not as reactive as the peroxyl one. In contrast, the peroxide destroyers, they take ROOH back to ROH, are species that are themselves oxidized by peroxides. These are sulfur or phosphorus compounds, so-called reduced sulfur, reduced phosphorus compounds, because they're both susceptible to being oxidized by many kinds of oxidizing agents, but particularly by peroxides. Reduced sulfur compounds are oxidized to sulfoxides or sulfones, depending on how far the oxidation process goes. Phosphines, like this compound triphenylphosphine, shown here, also react rapidly with oxidizing agents, and the product of that reaction is phosphine oxide. So these 2 classes of antioxidants act on 2 different classes of reactive oxidized agents. We chose to look at peroxide formation in B100. And there are any number of peroxide determinations. I think over the last 35 years, I've tried most of them, and even written a paper or 2 about peroxide analytical methods. But the one that we settled on seems to be the most effective and reliable is the so-called Biodiesel method that came out in 1996. And this depends on ferrous iron, iron 2, being oxidized to iron 3, ferric iron. And in the process, the peroxides are reduced to alcohols, ROH. And then the ferric ion that's formed reacts with thiocyanate anion to form a colored complex, very easily detectable and visible. Yes.
So yeah.
Well, you can put it in methanol. So we looked first at chain-breaking antioxidants. And this graph shows the different kinds of chain-breaking antioxidants we tested. We first looked at B100. It was a soy methyl ester, fairly pure, and we heated this at 60 degrees to induce the formation of peroxides and other oxidation products. The dark blue line is what happens when you heat the B100 by itself at 60 degrees. And within a couple of hundred hours, the peroxide formation goes from basically 0 to over 400 millimoles per kilo. It's pretty highly oxidized. So the chain-breaking antioxidants that act by quenching the peroxyl radicals that are formed. We did not test vitamin E itself, although we did test Trolox, the red triangles. Trolox is similar in structure to vitamin E, and it does fairly well. It slows the reaction down quite a bit, but eventually, after about 1,000 hours, it gets to almost the same level of oxidation. BHT, which you saw on the previous slide, is a little bit better than Trolox, but not much better. And ascorbyl palmitate, which is a vitamin C analog, is probably a little bit better still. But propyl gallate, which is shown in the top structural formula, turned out to be the best. Propyl gallate works again like the other peroxide radical quenchers, although it's not as sterically crowded, it is very reactive. And propyl gallate, represented by the blue squares, slows down the formation of peroxides for over $1,000, and then a slow process of propagation starts to develop. It still is pretty good for $1,500 or so at 60 degrees. We chose 60 degrees, although many kinds of oxidation tests are at higher temperatures, like the classic ransomat method that involves a special instrument that operates at 110 degrees is widely used throughout the industry. But when we tried to run the reaction at 100 degrees, the propyl gallate rapidly disappeared, and within about 48 hours or so, almost all of it was gone. This is on a log scale, so 0.5 represents half the material gone, or 0.7, I guess it is, represents half the material gone. So it's a very small fraction left after 48 hours. At 80 degrees, it also reacts fairly quickly, but at 60 degrees, it lasts for a good long while. Dittmar also wrote a paper a few years ago in which he pointed the same thing out, that certain classes of antioxidants rapidly break down at ransomat temperatures, and his paper is actually called The Limitations of the Ransomat Method. That's the reason he gives. Looking at the other class of antioxidants, the peroxide destroyers, when we add triphenylphosphine by itself to a biodiesel, a waste oil derived biodiesel provided by ISTC. This happened to have, at the time we tested it, a peroxide value of around 75 or so. And adding the triphenylphosphine destroyed almost all of it. So the peroxide value dropped down to about 0. But after heating at 60 degrees with triphenylphosphine present, the main thing that was observed was that the initiation period, or the lag period, was only delayed for about 24 hours, and then it took off and propagated at about the same rate as having nothing present. However, when the radical quencher, propyl gallate, was also added at the same time, there was a great improvement of the stability, whereas triphenylphosphine alone wasn't very effective. Triphenylphosphine plus a small amount of propyl gallate extended the lag period from maybe 24 hours to maybe 350 hours. A different biodiesel provided by the U of I in-soil program had a very high initial peroxide value, and by itself it went from maybe 175 to 350 in a short period of time. Adding low concentrations of triphenylphosphine, the sort of pink graph, the pink squares, didn't really help much. If you had a higher amount of triphenylphosphine, or a low amount of triphenylphosphine plus propyl gallate, there was further improvement. If you added a stoichiometric or equivalent amount of triphenylphosphine, you saw a delay of about 500 hours. But when triphenylphosphine and propyl gallate were added together, there basically was no formation of peroxides for as long as we could stand to test it. With other B100s, we've gone for much more than 70 days. Basically, running out of energy or money or something. Some of those B100s were stable for months. So, in conclusion, chain-breaking antioxidants work pretty well. Others in the literature have also said propyl gallate is very effective. Triphenylphosphine is not typically added to diesels or biodiesels as far as we know, but it does something when you add it. If you destroy the initial concentration of peroxide with triphenylphosphine and then add a small amount of the radical quencher, B100 oxidation is prevented for a long time under our conditions. And we believe that the initial peroxide concentration is very important under our conditions for assessing stability. Now I should point out that there are some limitations of this method. When you raise the temperature of a biodiesel or any kind of fuel oil, you have the result of decreasing the concentration of oxygen, because oxygen is more soluble in cold liquids than in hot liquids. And furthermore, at higher temperatures, there's no way to tell whether the chemical mechanisms of reaction at the high temperature are the same as those at the storage temperature. And the major limitation of these tests is that we have not tested the biodiesel that's most commonly used, which is low concentrations of biodiesel and high concentrations of petroleum diesel. And to really do a reasonable job, we would need to look at those fuels as well. We acknowledge our friends at ISTC for giving us money, for giving us B100, and for helpful discussions. Columbus Foods gave us the highly purified biodiesel. And the Insular program, as I mentioned, also gave us some biodiesel sample. So thank all these people, and thank you for watching and listening.
Thank you very much.
Are there any issues
that we do not test? We need someone else to do it. We don't have those facilities.
Are there any other questions with technical equipment?
Going back to one of your earlier slides where you talked about B100 and B20, the 20-80 ratio is based on mass?
Yes.
It is based on mass, okay. And then is the rating for biodiesel identical to the rating for like gasoline, like for example E85?
Well, I think the percentages are similar, so I say yes.
Does regular petroleum-based diesel have a deterioration curve also?
Mm-hmm.
How long does it last compared to biodiesel?
It's hard to say because many kinds of regular diesel have antioxidants added. DHT, we know, is added to some conventional diesel, so it would depend on how it's treated. But yes, there are compounds in conventional diesel that rapidly oxidate.
How about your canola oil at home in your refrigerator in the kitchen? Is that oxidized and turned into potassium?
Yeah, it will slowly at 0 degrees, at refrigerator temperature.
What I mean on the shelf, I don't know, say packing. Should you throw away any olive oil that's more than a month old?
We look for deposits because the oxidized products are not as soluble, so they settle up, and then you decant or
Is there good stuff on top?
good stuff will be on top.
Thanks,